Hi, my name is Christopher Hyatt, and this is my tape lab. So as a brief introduction, the purpose of this lab is to explore electric charge and measure it in a real-life applicable scenario. So three fundamental physics principles we're going to be using in this lab are equilibrium, the electric force, and the gravitational force. As a brief preview of the main result, um, the main result is going to show how we can use the electric and gravitational force to counteract each other and suspend something in a state of levitation. So in this experiment, we used two charged pieces of tape, and we used one to levitate the other, and then we um, used the force of gravity and that it was at a net force of 0 to calculate the charge on the tape. The initial conditions are just as seen in the image. There's not much except the initial conditions given it's an equilibrium problem. The system is going to be uh, the elevated levitating piece of tape, and the surroundings are going to be the tape below it, which is tape A, as well as the entire Earth, which has a gravitational force. So some logistics of the experiment are that the length of one of the pieces of tape is 0.14 meters, and given the conversion rate of 1 gram per meter, that makes it 0.00014 kilograms. The distance between the two tapes when the top one began to levitate was 0.021 meters. And then the gravitational force, because of the weight, and the gravitational constant was 0.0014 newtons. And then that means that the magnitude of the electric force was also 0.0014 newtons because it was in a state of equilibrium. And so using that, I was able to calculate a measured electric charge of 8.19 times 10 to the negative ninth coulombs. Next up, we have the code. First, we have the point model of the two pieces of tape, where the bottom tape can be seen as the orange dot, and the upper tape can be seen as the blue dot. And then the electric force from the orange dot is the orange arrow, and the force from gravity is the blue arrow. Some similarities and differences between the data and model are that this is obviously an extreme oversimplification, given that the tape is a long piece and we've just simplified it to a single point. Sources of error here include the oversimplification, measurements when I initially did the experiment, and then any kind of issues I may have made in the coding. Next up, we have the line model. This should be more similar to real-life data than the previous point model, given that it's more complicated and includes more factors. But sources of error include that it is still uh, a simplified version of real life because it only has 10 points for each piece of tape. But we can start to see here what we didn't see in the previous model, which is that the pieces on the edge are going to experience kind of like an outwards force because of the asymmetry of being on the edge and experiencing it from the entire long side of the tape. Some coding logistics is that the single point charge found the charge on one piece of tape to be 8.19 times 10 to the negative ninth coulombs. Um, and then the second model, which is the line of charges, found it to be 1.7 times 10 to the negative fifth coulombs. And then assumptions, approximations, and ideations made were that no charge was lost, the tape was made of finite points, and measurements were completely accurate. The what if question is electrons are negatively charged and protons are positively charged. What if the signs of their charges flipped? And I said that there would be no change in observations as electrons and protons are just subjective names we assign. The why question asks us to compare the two computational models as well as our experimental results of the charge on the tape, um, and which one is most likely to be closer to the real value. And I stated that the line coding charge is probably more likely to be more accurate than anything else because the point charge simplifies it more than that, and the experimental charge was subject to errors like mishandling, potentially, and just loss of charge to other surfaces. So the conclusions we gained from this were that the Electric force can be realistically measured using gravity as well as can be approximated uh, using code very effectively. Thank you.